Hello friends, good afternoon and welcome to the EduSat network. Our topic of discussion today is groundwater, and to talk about this, friends, our subject expert is also going to talk about the concept and principles in groundwater. And with this, I'd like to introduce him. He's here with us, Dr. S. Srikesh, Associate Professor, Center for Study of Regional Development, Jawaharlal Nehru University, New Delhi. And with this, I welcome sir to the studio and also request him to begin our today's lecture. Sir, thank you so much for being here.
Good afternoon, everybody. Today, I am going to discuss on the principles and concepts in groundwater. The lecture basically take you through the basic concepts in groundwater, and it also discusses what are the principles in assessing or understanding the groundwater resources. It is a concept. The concepts are explained and with the examples given in this discussion. Let's start the discussion with the groundwater. What is the groundwater? For a general person, the water which is available below the ground is called as groundwater. So, for a technical person, it is the water that is available in the saturated zone beneath the soil surface. That means the water that is occupying in all the spaces or voids present in the soil profile and in the geological units or geological stratum. That means in the lithology or in the rock which possess voids or the spaces or interstices occupy the water, and that water along the water which is found in the soil profile is defined as the groundwater. So, in general, a body of water that is found in deep aquifer zone that flows laterally and eventually merges with some surface water body. It could be an ocean, it could be a river basin, or it could be a pond, or it could be a lake, or any other surface body which is accumulating on the surface of the earth. So, basically the groundwater is that part of the water which is found below the earth's surface in the soil and rock particles in the zone of saturation. So, that means below the earth there is a zone of saturation where the groundwater is stored or accumulated, which is available to us. Now, these groundwater can have different origin. Normally, in general, most of the groundwater which we use today is part of the hydrological cycle. That means the water which is found on the earth's surface, which is circulated to the atmosphere and reaching back to the earth's surfaces through different atmospheric process or climatological processes, and which is part of the hydrological cycle, is the most important component of the groundwater. And that means this groundwater has two sources. Either it can come from the surface sources or it can be atmospheric, basically the water that is precipitated from the atmosphere. In addition to these two sources, that is the surface water sources and the atmospheric water, the groundwater also can be from other sources as well. That means one is the conite water. This is the water which is stored in the deep interior of the earth, which is not in contact with the atmosphere. That means in geological past or in the historical geological time scale, the water which is embedded within the rock, which is not in touch with the atmosphere, is called as a conite water. One of the important property of this conite water is that it is found in highly mineralized form, and major source of this water is basically from the ocean water, or it can be water which is from the atmosphere, which is embedded because of the certain earth processes which are operational in long geological time scale. In addition to this, there is another type of water which we call it as magmatic water, and in this water we have two types. Magmatic water means the water that is having its origin from the magma, and that water can be either plutonic water or volcanic water. In case of plutonic water, this water is found in deep interior of the earth, deep interior magmatic locations, and in case of volcanic water, this is forming part of the volcanic eruption or volcanic magma which comes to the surface at certain time when the eruptions occurs. In addition to that, we have the juvenile water, which so far has not been part of the hydrological cycle and it remained dominant, it is not circulated, it is not available to the use. And then comes the last type of ozone, that is the metamorphic ozone. That means the water that is participating in the metamorphic process, which is embedded in the metamorphic rocks and other rock types during the metamorphic process. So, in nutshell, these other forms of water resources may not be available to the direct use for the human purposes or for available to the plants for its photosynthetic purposes. So, basically today we are concerned about the groundwater which is forming the part of the hydrological cycle. So, we today in our discussion we only deal with the components which are the part of the hydrological cycle. That means the surface and the atmospheric part of the origin. That means the groundwater which is going to the interior of the earth from the surface of the earth or from the atmospheric precipitation. Now, coming back to the groundwater, there are different classification that is possible based on the saturation level or based on the permeability conditions, based on the aquifer type and based on the material in which aquifers are or the groundwater is found. Based on the saturation level, we have saturated areas and unsaturated zones of groundwater. Then we have three type of permeability conditions. According to permeability conditions, we can classify the aquifers into aquiclude, aquitard and aqueous. Based on the type of aquifer, we can either say that we have confined aquifers or we have unconfined aquifers. On the other hand, based on the type of material, we can call it unconsolidated material or unconsolidated aquifer, a semi-consolidated aquifer or consolidated aquifer. So, let us look one by one in each type of this types of aquifers. Based on this saturation, either we classify them saturated zone and unsaturated zone. Here basically we are dealing with the vertical distribution of groundwater sources. In the unsaturated zone, otherwise known as the zone of erosion, the water occurs in the soil surface and it is the topmost zone of the saturation. That is, above the saturation level we will find this unsaturated zone where you find the voids filled with the water and air. That means in the soil profile you will find water as well as air, because soil has three components. You have the solid soil material, you have the interspaces between the soil material which is either occupied by the water or by the air. And because of this this ability of the soil to accommodate both water and air, the proportion of the water which is held within the soil profile changes with the time, because the water can replace the air and occupy the places of the air too, provided there is sufficient availability of water infiltrated to the soil profile. And this happens at the time of precipitation, and when precipitation exceeds the ability to infiltrate, then the soil becomes saturated with the water. So, over a time scale or a time period, when precipitation continued to occur, then the water becomes saturated with the soil becomes saturated with the water, and that water infiltrates further to reach the deeper layers of the soil and get accumulated at the saturated zone. Now, this unsaturated zone extends from the surface of the earth or surface soil to the bottom of the soil profile just above the unsaturated zone. And in this unsaturated zone, you have a soil moisture layer within the root zone. And that is why the unsaturated zone is important for the operation of agriculture or availability of water for the plants and crops. So that's why for the agricultural operations, the soil scientist gives utmost importance to this zone of the groundwater, which is normally called as unsaturated zone. And this unsaturated zone is further divided into three layers, and that layers are known as soil water zone, vadose zone, and the capillary fringe zone. These three zones together also is known as zone of aeration, and this zone of aeration basically consists of interstices or pores which are again filled with the water or by the air depending upon the saturation level. And the topmost layer of this aerosonation is the soil water zone, and this is basically goes up to the rooting zone or root depth zone where the plant's roots are extended. So here the moisture availability is highest among the three zones present, and immediately after this soil water zone you have the vadose zone, that is the intermediary zone between the soil water zone and the capillary fringe zone, and this extends beyond the soil rooting depth. Vadose zone extends beyond the soil rooting depth, and then in the last zone is that capillary fringe, wherein water from the saturated zone come to this zone of aeration because of the capillary action or capillary forces. So there is a capillary forces which operates in this area, wherein the water from the saturated zone gradually moves to the capillary fringe, and this capillary action continues. Some amount of water or the moisture may even reach to the vadose zone. So this water is available to those plants which have a very great depth of roots, or the phreatic zone which we call it as, where the plant have greater depth roots to reach this up to this depth, and then use those water for the photosynthetic and other water requirements of the plant. And among these three zones, the topmost zone, that is soil water zone, can be temporarily saturated with the moisture. That's because the precipitation infiltrate the water to the soil profile, and this infiltration lead to the percolation of the water to the lower layers of the soil, and that results in temporary saturation if there is a continuous addition of water to the soil surface, and there is a continuous infiltration process going on, and that depends upon the connectivity of the pores which are present in the soil profile. So the movement of water through these zone, the soil water zone, ultimately decides the amount of water that is recharged, and that is also reaches the groundwater sources. Now let's look at what happens in the saturated zone. This is the zone which is below the zone of aeration, and here the water is completely occupying all the pore spaces or interstices present within the soil profile or in the rock particles or rock unit or the litho unit. And in this zone, the pressure head of water is greater than the atmospheric pressure. On the other hand, at the water table, which is the topmost layer of the saturation zone, the water is at the atmospheric pressure. That means there is a pressure difference between the water table, which is the topmost layer of the saturated zone, and also the layers below that. That is higher. As you go down from the water table towards the saturation zone, you will find that pressure is gradually increasing. So what we can say is that a surface that is determined by water level measurements made in wells that penetrates only a short distance into the saturated portion of an unconfined aquifer consists of this saturated zone. So this saturated zone depends upon the availability of water. That means if the saturated zone is at shallow depth, you can reach the groundwater sources immediately with a lesser effort and with a lesser cost. On the other hand, if the saturated zone is found in the deeper aquifers or deep layers of the soil, then the cost of extraction will be greater and effort to or energy use of extraction will be great. Hence, the availability of water will be at a higher cost. So, this factor, the depth at which the saturation zone is found, determines the availability of water either for drinking purpose or for the irrigation purposes or for mining operations as well. Suppose if the water is found at greater depth where the minerals or the fossil fuels are found, there is a possibility that higher cost will be incurred in extraction of those resources and minerals, because there is a presence of large quantity of water in this area. Now, the zones in which there is a saturation or saturation of water is occurring, which we call it as aquifer. That is, the zone in which the water is saturated within the soil profile is called as aquifer. So, it can be a soil or it can be a rock layer. So, more clearly we can define that a water bearing porous soil or a porous rock strata that yield significant amount of water to the wells or other water bodies can be called as an aquifer. So, there is two property for an aquifer. You should have sufficient amount of water present, and that amount of water is available to the wells if we are digging a well to that aquifer. That means it should give a significant yield of water to the wells. So, this is what it qualified to be called as an aquifer, the ability to store water and yielding good amount of water to the wells if it is reached up to that depth. So, in more geological terms, we can say that it is a geological formation that contains sufficient amount of saturated material or permeable material to yield sufficient amount or quantities of water to the well and springs can be called as an aquifer. So, there is ability to store water, there is ability to transmit water, which qualifies to call a rock as an aquifer. And it can be a saturated zone or an unsaturation portion of the litho unit. Not necessarily that all the aquifers are always saturated. There can be periods where the aquifers are unsaturated also. And these are called water bearing formations, or sometimes it is also called as groundwater reservoirs. So, aquifers is also known as the groundwater reservoirs and also otherwise known as the water bearing formations or litho units. Now, the aquifer types. The classification of the aquifers is possible based on different characteristics. One is based on the type. All aquifers are not showing the similar properties. There are variations in permeability, there is a variation in transmittability of this water, and there is variation in interstices and opening present in the rock or the litho units. So, based on these properties, the variations in permeability and conductivity or holding capacity of the aquifer, it can be classified into three types, namely aquicludes, aquetarts and aquefuge. The aquicludes is any rock which is have the capacity to bear the water that are effectively impermeable. What does it mean? That means the water, the rock or the soil strata can hold the water, but then that strata or that unit may not be acting as a effective permeable area. So, effectively they may be acting as a impermeable strata. For example, shales is a good example, or thick clay is a good example. Clay can hold lot of water, but then it is not possible for the clay to effectively permeate the water through the layers. So, it's a type of aquifer. We call such type of aquifers as aquicludes. They are saturated, but relatively they are impermeable. And if you try to extract water from these sources, this does not yield appreciable quantities of water to the wells. So, that is why we call it as aquicludes. It reduces the flow or retards the flow of water in the aquifers. And the other type of aquifer is acutard. This is the geological strata that is slowly permeable, and it impedes or it retards the groundwater movement within the aquifer. This aquifer also may not produce sufficient quantities of water if you dig a well to this aquifer, and there is less yield to the wells if we have wells in this type of aquifers. So, the movement of water is reduced or retarded in this type of aquifers. It may transmit some amount of water with the adjacent aquifers, and this type of aquifers are found in silt or mudstone or sandy clay. So, this sandy clay or mudstone can be classified or called as an acutard, because there is some amount of permeability, but that is not enough to give a free water to the wells. And the last type is called aquifage. Aquifage is basically that type of rock which is incapable of either absorbing or transmitting water. That means neither this type of aquifer can absorb water, or it is not in a position to water through its profile. So, basically it acts as a storehouse, or it can prevent further movement of water either laterally or vertically through the rock profile or through the soil profile if that type of rocks or aquifers are present. Basically, good example of aquifage is that granite. Granite is an impermeable layer. So, if the water infiltrates and reach up to the granite, is tend to remain accumulated above, and this aquifage normally tend to be a confining layer where the movement of water is almost restricted. Now, based on the exposure to the atmosphere, the groundwater can be, or the aquifer can be classified as unconfined aquifer and confined aquifer. So, there are two types of aquifers, which is one is unconfined, there is no confinement in this case. Another is the confined aquifer, where the water is held within a confined layer. So, let us look what is an unconfined aquifer. I would like your attention to the following diagram, which is shown in the screen. You can see that there is a layer of water which is found above an impermeable layer. If you look at this, layer which is shown in gray color, this is a impermeable layer, or it is a confining layer, and this confining layer holds water above it, and that is called as the unconfined aquifer. The water which is there at that place is known as the unconfined layer, and water table varies in this unconfined layer, because the infiltration of water from the above varies with the time. During the monsoon month, when in case of India, when the water availability is high and the infiltration of water through the soil profile is high, there is a lot of recharge of water to the unconfined aquifer, and in this case the aquifer water or the unconfined aquifer layer increases its depth or height, and hence the water level in the unconfined layer always will be fluctuating. It will also vary because there will be some amount of discharge to adjoining aquifer systems or some surface water bodies when the water level increases. So, naturally there will be a decline after the recharge period is over, and then it come back to an original position. In case there is an extraction, this unconfined aquifer water level further goes down, and there will be replenishment only during the following monsoon season or the following rainfall season. So, there is what it shows is that the unconfined aquifer layers shows high variation in water level, and it changes with the season. And in this case, the water table or the uppermost part of the aquifer, that is unconfined aquifer, this portion is known as the water table, and this water table is at the atmospheric pressure. And this happens because there are openings within the soil profile, and that openings allows the air to be in contact with the water, or the water in the topmost layer of the unconfined aquifer is in contact with the atmosphere, hence it attains the atmospheric pressure. And another feature which we can normally observe in certain areas is that what you call it as a purged aquifer or purged water table. As is shown in this figure, you can see that this is a confining layer. There is a gray layer depicted in gray, or litho unit which is depicted in gray, and above that you have a blue zone which is water. And this gray zone is basically a confining layer or a impermeable layer where the water is not allowed to penetrate below that layer. So, water get accumulated and accumulated in this area, and it is a local aquifer above the unconfined aquifer. And the water capacity or water holding capacity in this in the purged water aquifer or purged water table is relatively lesser, and that's why if you dig a well to the purged water table, it may or may not have water throughout the year. That depends upon the total holding capacity of the purged water table. And normally this purged water table are found above the unconfined aquifer layers, and they yield lesser water to the wells than the confined and unconfined aquifer layers. And you will find below the unconfined aquifer, you will find another layer which is denoted as confined aquifer layer, and this confined aquifer layer has two impervious layers. One is above it and another is below that. The above one confines this aquifer, that means prevents the infiltration of water from above. So, directly the water is not infiltrated to the confined aquifer, it is through the indirect recharge the water is reaching the aquifer. So, in case of confined aquifer, both below and above you have a impervious layers. So, it limits the water's movement through these layers. So, this layer get recharged in a distant area where there is an exposure to the atmosphere or soil. So, the recharge zone for this type of soil is also limited, where this confined zone get exposed to some other strata or some other surface area. Now, if you look at this figure again, you have a area where there is no direct infiltration. In this area there is no direct infiltration of water possible, whereas only in this area there is some amount of recharge possible in this confined aquifer. So, it is completely separated. This zone is completely separated from the atmosphere. There is no direct interaction between the confined aquifer water and the atmosphere above that. So, it is basically it does not have a water table, and the water here is contained under sufficient pressure that water rises above this aquifer if there is an opening above to the surface. Because of its confined position or confined nature, the recharge potential of this confined aquifers are very limited. It can vary from say 5 to 20% only. So, in case of recharge potential, such aquifers have lesser potential. So, normally this confined aquifers are found in greater depth in the aquifers or in the soil profile. Now, another feature which we need to note in this diagram is that, which is, if you notice on the right hand side point of this diagram, you can see an artesian well. Okay. To explain this concept, let me talk about the potentiometric surface. The potentiometric surface is that a line joining places having equal hydraulic pressure. As I mentioned earlier, the confined aquifer is under great atmospheric or hydraulic pressure, and the pressure level or pressure head is where the maximum water level is there. In this case, it goes to the water table where it is exposed to the atmosphere, and this is the maximum water head, and the potentiometric surface is an imaginary line which joins the places having same hydraulic head, and this hydraulic head is because of the pressure head exerted by the confined aquifer. And now, if there is an opening of a well to this confined aquifer, the water can rise up to this level of hydraulic head. Okay. And if you consider this, on the other hand, which is written as flowing artesian well, the well opening is below the potentiometric surface. Hence, because of the hydraulic head, the water comes to the surface and flows. For example, spring could be a best example of this kind of a flow, where it may be the confined aquifer may be having higher hydraulic head above the spring exposure to the atmosphere. Hence, there could be a free flow of water to the surface. On the other hand, the other artesian well, the well opening is well above the potentiometric surface. There is a difference, this much difference between the potentiometric surface and the artesian well opening to the surface. Hence, the water level is below the well opening, and it reaches above the unconfined aquifer layers under the natural pressure conditions. So, depending upon the hydraulic head, it is possible for us to obtain the water from confined aquifers either under the natural flow conditions or under the natural head with a less energy to the surface. So, if we judiciously use this confined aquifers are better for us, because it is more safer than the unconfined aquifers, because unconfined aquifers have exposure to the surface and there is a possibility of contamination. Okay. Now, another type of aquifer or another type of classification of aquifers is in terms of the type of material in which they are formed. So, based on the type of material, we can say that there are unconsolidated aquifers and the semi-consolidated formations in which aquifers are found. In case of unconsolidated aquifers, it is basically made up of highly porous material. In this, there are a large number of openings or pores or interstices in which the water is stored. So, there is a high potential for groundwater storage, and because of the high potential, there will be high annual replenishment of the groundwater. And this unconsolidated aquifer or the formation where the water is stored can have two recharge zones. One is active recharge zone, and another is passive recharge zones. The active recharge zone is the zone in which the fluctuations in water level occurs because of the annual replenishment of groundwater and natural depletion of groundwater because of the gravitational flow of water. In case of passive rechargement, passive recharge zone, such recharge, such fluctuations are minimal, and they are normally found below the fluctuation zone or fluctuation level of the aquifer systems. And such unconsolidated aquifer systems are found mainly in alluvial zones or in the deltaic areas or in the coastal areas, and also in the sedimentary deposits. Such zones, for example, in India we have Ganga and Brahmaputra zones or river basins where lot of unconsolidated aquifer systems are found. And the second type is related to this, which is called semi-consolidated formations. This is found in fault valleys because there are a lot of fissures, joints, and other structural formations which can hold water or held water within the profile. So they are called as semi-consolidated formations. In these systems we can also have free-flowing wells. For example, in case of Kodallur sandstones or in case of Gondwana systems, we can find such semi-consolidated formations. The third type is that of consolidated formations. These are also known as fissured formations because they are normally found in structurally weak zones of the litho units. They have a least porosity, that is primary porosity is very least in this type of formations because the storage capacity is associated with the structural or the lineaments formed within this rock, that is the fissures, joints, and faults formed within the litho units. They can also have medium to low capacity to store water. The examples of this type of rocks are the igneous and metamorphic rocks, excluding the volcanic and carbonate rocks. In addition to that, even volcanic and carbonate can also be considered along with the consolidated sedimentary rocks as the examples of this type of rocks. In India, about 2/3 of the total formations found or aquifers found in India are of this type. Now, the groundwater flow within the aquifer system is because of certain forces acting on it, or because of the differences in influence of energy within the profile of the aquifer. Based on that, there are 3 types of energy available for the water to flow from one part of the aquifer system to another part of the aquifer system, or from one aquifer system to another one. So, under the influence of energy, we can have elevation energy, we can have a pressure energy, we can have velocity energy. That elevation is because of mere presence of an aquifer system in a higher altitudinal area. From that area, it will flow to a low altitudinal area, then that is a natural elevational flow. And second is because of the pressure difference, which I discussed earlier in the graph or in the image, where I shown you the pressure difference or the potentiometric surfaces, difference in potentiometric surfaces and the altitude of the place, and because of that you have the pressure energy, and then you get a velocity energy, which is because of elevation or pressure energy. There is a movement of water, and that movement of water is depending upon the pressure difference or the elevation difference. So, the velocity energy is basically attained because of elevation or pressure energy levels. Now, the occurrence of the groundwater is also contingent upon many factors. One is that of geological factors, that is basically the litho units, the rock types found in an area, because the rock type decides the nature of voids present or interstices present in that, and it also determines the size of the pore shape of the pore and distribution of the pore, both aerially, and that means the horizontal and vertical distribution of these voids varies with the rock type. And there could be variation in the intergranular spaces and massive spaces, again determined by the rock type. So, in addition to the litho characteristics, then you have the porosity characters, that is pore spaces present within the formations or the aquifers. Whether they are small in size or large in size determines the holding capacity or the quantity of water that can be stored within the aquifers. And the massive spaces, that is basically the large blocks of rock, such as having fractures or fissures or bedding planes, have large spaces present within the rock profile or this litho units, and they also can hold sufficient quantities of water which is available to the people for usage. So, based on that, the occurrence varies. So, for example, I can show you a map basically depicts the hydrogeological conditions. In this map, we have different layers: unconfined aquifer, confined bed, and the confined aquifer. So, basically you have two zones, one is the saturated zone, another is the saturated zone, another is the unsaturated zone. And this saturated and unsaturated zone can be classified into unconfined aquifer, which is having exposure to the atmosphere, and a confining bed, which prevents the infiltration of water from the surface to the lower layers, and you have a confining aquifer where the water is stored. In this case, it is a limestone area where the water is stored, and the confining is the clay, which is having very low pore spaces. So, the movement of water through this layer is limited, and above that you have a water table, and you can see that the water is stored above the clay layer, and you can have if you dig a well, it can have sufficient quantities of water, and if you dig a well to the limestone area, it will result in an artesian well formation. Now, if you see this different layers, you can see that, as discussed earlier, the space of pores is least in this case and more in the limestone areas and in the unconfined zones. Similarly, if you see in this clay zone, there will not be any massive spaces because it's a clay layer. On the other hand, if you see the limestone zone, there could be a lot of massive spaces which can hold a lot of water. Now, the groundwater flow in these layers under the different hydrogeological conditions depends upon the hydraulic head present in this area. That is, whether it is a pressure head or elevation head, which I discussed earlier. In addition to this, it is also influenced by the gravitational flow. That is, the movement of water through the soil profile because of the soil profile or the litho unit because of the gravitational pull of the earth, or it is also governed by the difference in potentiometric surfaces. That is possible only in case of confined aquifer. In confined aquifer, because of the pressure head created because of the water level or elevation head, there could be variations in potentiometric surfaces. If you have a high potentiometric surfaces, there will be a greater flow of water to the lower reaches or towards the lower side of the potentiometric surfaces. And basically this potentiometric surfaces shows the lines of equal energy, and based on this equal energy, we can determine the amount of groundwater that can flow through that zone. So, basically the movement of water within the aquifer zone can be mapped in terms of flow line, which indicates the path of the particle of water that makes through the flow field. So, if you go to near to a river, if the water table is near to the water, then the flow will be from the aquifer to the river. On the other hand, if the lean season or during the lean season, if the water table goes down, the flow of water will be reversed, that is from the river to the aquifer system. So, during the monsoon system, because during the monsoon period, because the water table is coming to near to the surface or at the surface, the flow will be from the aquifer system to the water, maybe river or a lake. On the other hand, the flow will be reversed because the water level goes down during the lean months. Now, there are different forces acting on the or controlling the movement of water through the aquifer. One is the capillary force, second is the gravity force. The capillary force, which I discussed earlier when we discussed about the unsaturated zone, is basically because of the physical attraction of soil and rock particles to the water. And because of that, when water moves from high potential zone to low potential zone, that means from a region of high water availability to a region of low water availability. So, there is a movement because of that is against the gravitational attraction. So, the water move up in the soil profile. On the contrary, the water moves down because of the influence of gravity, and it is also because there is a variation in force spaces among this. Normally, as it goes down in the soil or in the aquifer zone, there will be a reduction in pore spaces from higher number of pore spaces to lower number of pore spaces, and it will be negligible towards the lower reaches of the aquifer. So, it can go as low as 600 numbers per unit area in case of the pore spaces. The flow is also controlled by or influenced by hydraulic gradient and also the cross-sectional area through which water is flowing, and also because of the permeability of the zone in which it is moving. This concept has been explained by Darcy, and in his law he states that the saturated flow of water through the porous media is proportional to the hydraulic conductivity and permeability of the medium. And flow, that means flow is proportional to the head loss, that means difference in water potential between two places, and inversely proportional to the thickness of the medium, that is thickness of the aquifer. So, it is clearly he states that the flow, that is rate of flow of water through an aquifer system, is dependent upon the hydraulic conductivity, cross-sectional area, which is determined by thickness of the material and width of the cross section, and also by the change in water head and length of the media through which it is flowing. So, this stipulates that, or Darcy's law stipulates that, the flow is controlled by the hydraulic conductivity of the material and also by the permeability of the medium. With that, I would like to conclude today's discussion on groundwater. If you have any clarifications or doubts, we can discuss now.
Right. Thank you so much, sir, for this very interesting and informative lecture that we had today. And of course, since we have some time left, sir, I would like to pose a few questions that have been sent from some students. And sir, in your lecture, you discussed and you talked about different types of aquifers.
Yeah.
So, could you tell us which are the common ones which can be found in India?
In India, I talked about three types of aquifer systems. One is consolidated, semi-consolidated, and unconsolidated. The mostly nearly 2/3 of India is having consolidated systems, whereas large potential is found in unconsolidated systems.
Right.
For example, in case of river Ganga, all along the course of the river, on both sides of the river Ganga, we have extensive areas of unconsolidated.
Right.
Similarly, in the course of Brahmaputra river, also we have extensive areas of unconsolidated formations. And in addition to that, we have the coastal areas,
Right.
large extent of coastal areas, where large number of rivers are joining the sea. And these areas, we call it as deltaic area, is having large potential of unconsolidated.
Right.
In terms of formation and in terms of capacity to recharge
Right.
and replenish, these are the large areas where we can have large potential for exploitation of groundwater resources.
Right. So these are places where you can find aquifers. And very briefly, sir, I would like to ask you, when we talk about groundwater, of course, it seems like a very broad area, but is a lot of research or is any kind of research going on in this area, which the students would also say would like to take up as potential areas?
Of course, it's a this is a very interesting area to for the students to carry out research activities. See, there are broadly two areas in which students can look into. One in terms of the quantity variations, what availability variations over space and time, how the groundwater availability varies over space and time. What are the factors influencing such variations in groundwater availability? How this variability can be or fluctuations can be minimized, or what are the factors one should take into account while using these aquifer systems or extracting these aquifer systems. On the other hand, the research can look into the qualitative aspect of it, whether these aquifer systems are still found in pure form or there are contamination happening. Is it because of the natural lithological contamination, as in the case of arsenic pollution in eastern part of India, or it because of this man-made influence, that is means over-exploitation of groundwater resources, or because of the contamination from the surface sources, where the industrial effluents may be reaching the groundwater sources. So it is possible for the students to look into all those aspects of it, and there are different techniques available nowadays to understand this phenomena, and models are available to exploit further into that.
Right. Thank you, sir. And of course, you have pointed out some areas which research is happening in and could probably also happen in. But also, if you look from a general point of view, when we talk about groundwater, it becomes a very significant thing, a resource that we must say harvest. Or also, probably some NGOs are also working on harvesting the groundwater. So, are some kind of research happening with them, or these are just independent researches?
I think the research or the studies are happening at both. One is on academic level,
right,
and another is maybe an action oriented. I would like to call it as action oriented research,
right,
which is basically spearheaded by NGOs and other research interested people. So both level the interests are there, and the research activities are being carried out. The good aspect of the action oriented research is that they just don't confine to the theoretical aspects of it. They
right,
look
yes,
more from the management point of view
true,
and utilization point of view. So there
right,
are large scale or even interventions which is happening. Not only interventions, they are also creating large scale awareness among the people how to use groundwater resources. What are the things one should take
right,
care of while understanding or while studying these resources,
right,
or exploiting these resources.
All right. Thank you so much, sir, for talking to us about this. And of course, just to let you know, viewers, that we are going to take up this idea in another lecture of ours, where we talk more in depth about
the management
groundwater,
issues,
the management issues related to the same. So thank you so much, sir, for being here today and sparing your valuable time. And thank you again, viewers. Have a wonderful day ahead.